Good afternoon. Um, uh, Spring has hit California. You can see that I am wearing one of my Hawaiian shirts, unlike the button-downs that I recorded the lectures in. So everything's feeling good. And in this video, I'd like to discuss a few questions that have arisen in the discussion forum and that I think may represent common misconceptions. First, I want to remind everyone to be aware of the types of things that we discuss, strings versus characters, and so on. Then I want to point out a subtle difference between an automaton accepting a string and accepting a language. And finally, there are a few interesting edge effects that we need to understand. You may have heard of the Zen koan, "What is the sound of one hand clapping?" I don't know. But here we face a harder problem. Under the sound of no hands clapping, I want to remind people what it means, for example, to compute the sum of zero integers. We're familiar with types or classes from work with most any modern programming language. The things we talk about in automata theory also have types, and confusing one type for another is just as dangerous here as it is in programming. Two distinctions I want to emphasize today are, first, between characters and strings, and then between sets and the members of those sets. A string is a sequence of 0 or more characters. In most programming languages, double quotes are placed around a string, and single quotes around a character. The distinction is most important when the string is of length 1, because then it looks just like a character if you don't do something like double quote it to indicate its type. Most importantly, epsilon is the way we represent the empty string. In most languages, the way to represent the empty string is by double quotes with nothing in between them, like this. And I think most confusion occurred when people noticed that in an epsilon NFA, some arcs are labeled by the string epsilon, while others are labeled by input characters or input symbols. Previously, DFAs and ordinary NFAs had all arcs labeled by characters, but epsilon is not a character, and yet we appeared to use it where you expected an input symbol, that is, a character, to appear. But there is no real problem, since a character can be coerced to be a string of length 1. It's in fact very natural in programming languages. For example, in Java, an easy way to convert characters to strings is to write the empty string concatenated with that character. Since characters are coerced to strings, the character, say 0, is converted to the string 0 and concatenated with the empty string, which leaves just the original character but converted to a string of length 1. So for an epsilon NFA, just think of the characters labeling the arcs as strings of length 1. Then you can concatenate the epsilons and characters along any path and get a string naturally. As with any kind of automaton, the sequence of labels along any path is of type string. Here's a pretty picture of a path in an epsilon NFA. It doesn't matter whether the states are distinct or if some repeat along the path. You just concatenate the labels. Epsilon, the string 0, the string 1, string epsilon again, string 0. The concatenation of these 5 strings then is the string 0, 1, 0. Now let's move on to sets and elements. Elements come in many different types, for example, integers, strings, characters, and so on. Sets can have elements as members, so for example, a language in the world of automata theory is a set of elements of type string. That is, the type of a language is set of strings. And remember that epsilon is a string, while the empty set is a set. There is a notion of membership that relates a set to the members of that set. A set can have members. The element types like string do not have members. Technically, the members of a set can be sets themselves, but we're not going to talk about such sets much. Occasionally, we mention the power set of a set S, whose members are each of the subsets of the set S, and thus are sets themselves. But in most cases, you can assume that sets have members that are elements and not sets. The empty set is a set, but it has no members. All other sets do have one or more members. And elements do not have members either. For example, epsilon has no members, but the reason epsilon has no members is because it is of a type for which having members makes no sense. We must not confuse the empty string with the empty set. They each have no members, but for very different reasons, and their types are not the same. Let's see how the set-element distinction applies to states of a non-deterministic finite automaton. First, states of any automaton are elements, not sets. The subset construction seems to create a DFA whose states are sets of the states of the NFA. But really, what we are doing is computing sets of NFA states and giving each one a name. This name is the name of a DFA state, and each DFA state corresponds to a set of NFA states, but the DFA state is an element with an associated value, and the value is the set of NFA states. We can even use the set of NFA states as the name of the DFA state, but we should then understand the notation for the set. Like the set containing P and Q, this, is a string that is the name of a DFA state. Here's another point that has caused some confusion. Automata accept strings, the labels of the paths that lead from the start state to an accepting state. But we also said that an automaton accepts a language. This language is the set of strings that the automaton accepts. If we say automaton A accepts language L, then we mean that L consists of all and only the strings that A accepts. Thus, while the typical automaton accepts an infinite number of different strings, it accepts exactly one language, the set of strings that it accepts. Let's remember that the phrase automaton A accepts language L means that L is the one language of A. A accepts all the strings in L, and A does not accept any other strings. The extreme case of the confusion would be an automaton like the one shown, which accepts every string, but only accepts one language, the one we refer to as 0, 1 star. That's this. That is, it's the language of all strings of zeros and ones. If you don't see the difference between accepting strings and accepting a language, you would erroneously conclude that this automaton accepts every language whatsoever, such as the set of 0 to the n, 1 to the n, such that n is equal to greater than 1. It doesn't. It accepts this language, set of all strings of zeros and ones. I now want to talk about a point of confusion that comes up in several places. What happens when you try to apply an operation to zero things? For example, we know what it means to sum 2 integers or 10 integers, but what if we are asked to sum 0 integers? Or if I have a string of zeros and ones, it makes sense to ask whether the string has an even or odd number of zeros. But what if the string is empty? So, for example, 4 plus 7 plus 3 equals 14, no problem. If I just want to sum 4 plus 7, cross out the 3, again no problem, that's 11. If I just want to sum the 4, no 7 there, fine, that sum is 4. Now, if I take the 4 away, what's left? What is its sum? I claim that in general we should take the operation applied to nothing to be the identity for that operation. For some, the identity is 0. That is, 0 plus anything is that other thing. This is a well-accepted convention. I can't prove to you that the sum of 0 things must be the identity 0, but neither have I seen a reasonable justification for any other convention, And if you have one, it would be a great topic for the discussion forum of the class. And it is natural and intuitive, as we can see, if we write the obvious code to sum the n elements of an array. Here's what the code looks like. You initialize the sum to 0, there, and then go through the array in a loop, and you go through n times. You'll get the correct sum for any n equal to or greater than 1, but what happens if n happens to be 0? If that's the case, you never execute the loop, you just jump right around it, and the sum is left at 0. And initializing the sum to anything but 0 makes no sense and would not give the correct result for n equal to or greater than 1 unless you did serious contortions to the code. Here are some other examples where the identity for the operator is the only thing that makes sense. The OR of zero propositional variables is false because false is the identity for OR. That is, false OR x equals x. Similarly, the AND of no propositions is true because true AND x equals x. The product of no integers or reals is 1 because 1 times x equals x. And if we concatenate 0 strings, we should get the empty string, since epsilon concatenated with any string x is x. As an example of why the convention for strings makes sense, look at an automaton where the start state is also an accepting state. This automaton has more to it, I just didn't draw it. There is a path from A to A that goes through no arcs. It is of length 0. In general, the string that labels a path is the concatenation of all the strings that come from the input symbols along that path. Again, remember that the characters labeling the arcs are converted to strings for concatenation. But in this case, the path has no arcs, so its label must be the concatenation of 0 strings, that is, the empty string. That's great, because it means that the empty string is accepted by this automaton. And since the automaton starts out in an accepting state before it reads any input, that makes sense. Next, let's look at the question of whether 0 is odd or even. Curiously, this question causes a great deal of disagreement. For example, I remember one day in 1973 when we had gas rationing. You could only fill up on a day whose number was even if the digits on your license plate formed an even number, and ditto for odds. But what if your license plate had no digits, a vanity plate like lover? Okay. Since legislatures are not mathematicians, different states had different policies, some treating a plate like this as odd and others as even. But we know that 0 is even because it leaves remainder of 0 when divided by 2. That is, 0 is 2 times an integer, namely 0 in this case, plus a remainder of 0. And anything that leaves that is of the form 2 times any integer plus 0 is even. Now the empty string has 0 of every character, and 0 is even. So if we ask a question like, does the empty string contain an even number of some character like 0, the answer is yes. And if we ask whether it has an odd number of zeros, the answer is no. Okay, and here's a bonus answer. Okay, few people actually use automaton and automata correctly. Let's learn to be pedants and use them right. Okay, automaton is a singular noun and it's plural, and a regular plural because of its Greek origin is automata, one automaton, 2 automata. But it gets worse. Okay, everybody says automata theory, never the singular form automaton theory. But other theories use a singular form of the noun that describes what they are about. For example, physicists talk about string theory or quantum theory, never strings theory or quantums theory. Well, that should be quanta theory anyway, since quantum is another irregular plural. And Don't ask me why. Anyway, see you in class.